here Petra Schwer from Karlsruhe, and she is going to speak about the combinatorics of Coxeter groups and Affine Deligne Lusztig varieties.
Turn on my microphone. Thanks for the introduction, and thank you very much for having me here as a speaker. As you said, I'm going to talk about combinatorics of Coxeter groups and their relation to Affine Deligne Lusztig varieties. So here we really have two worlds meeting each other. So on the one hand, we have geometric group theory, methods from there, combinatorics in Coxeter groups, and on the other hand, we have a very much algebraic object coming from algebraic geometry and motivated from questions there, which is the Affine Deligne Lusztig varieties. So almost all I'm going to say today is joint work with Milicevic and Anne Thomas. And I'm going to start with the geometric side, so talk about Coxeter groups first, and then introduce you to the Affine Deligne Lusztig varieties, kind of motivate what they are, and then show you how the combinatorics can be used to solve questions about these algebraic objects. So let me quickly remind you what Coxeter groups are. So they're defined with the following presentation. You have a generating set, capital S, and elements little si in there, and then you put a bunch of relations. So first of all, these are abstract reflection groups, so each of the generators should be squared the identity. And then if you multiply two of them, you have an integer mij that tells you what order the product has. So there's slight conditions on the mij. They're greater or equal than 2. Well, they're 2 exactly when you, no, not exactly, but in particular if I equals j. But they also can be equal to infinity, and here equal to infinity we mean there's no relation between Si and Sj. Okay, so you get a matrix describing these exponents. Let's have a look at two examples we will keep looking at throughout the talk. So these Coxeter groups, they come in 3 classes. They're reflection groups on spheres, affine space, or hyperbolic space, and the 2 ones we're interested in today are the ones acting on a sphere and on affine space. We'll totally ignore the hyperbolic ones for the sake of this talk. So the 2 examples we're looking at, well, it's a spherical one, say this one, generated by 2 reflections, S and T, and the product of their order is 3. So what you get here is a group acting on the one sphere, and you have 2 orbits of vertices here. So you get this hexagon whose vertices are separated into 2 classes. And this spherical example fits naturally into an affine example, meaning it's a subgroup of an affine reflection group. I try to get this as neat as possible and failed. Well, never mind. Okay, so here you've all seen this before. It's the tessellation of the plane. It should be the tessellation of the plane with equilateral triangles, and I messed it up here. Okay, that's good enough. So here, say here's the origin. And we can again look at this group generated same way here by S and T, S here, T here. And then what you see is just you have, again, your little sphere around the origin. on which this group, say W0 from over here, acts at. But you can also make this group bigger by adding a third generator R on the third side of this triangle here, which is the fundamental domain of your action. And then this W becomes generated by RST, where any pair has order 3 and all the generators, of course, squared become the identity. So xy cubed equals 1 means any pair x different from y in the set RST, in the product to 3 is 1. Okay, so you have this affine group here, and your spherical one fits in naturally, but not only that, actually this group here is isomorphic to the semi-direct product of the spherical group and the translation group. So I said here, imagine here's the origin, then you can generate a translation group with these two little arrows here, and these red ones, that translate your origin to here and here. And what you get is a bunch of red vertices in this plane, so that if you draw a hexagon, a red one, around each of these red vertices, then you have another tessellation of your plane, now by hexagons. Okay, so in each triangle in this plane is contained in a unique hexagon, so it belongs to a unique translation, and then has a unique one of these spherical local orientations. So elements, let me put this down here, W in W can be written as a translation to the point lambda, say lambda's here, and then times some u, where u is the local spherical direction at your point lambda. So here, this would be t lambda times u, where u is this u over here. Okay, we make heavy use of this way to present the little elements in this plane. That's why I'm spending lengthy time at the beginning to talk about this. Okay, let me state a problem about Coxeter groups, which is easy to formulate, but not that much progress has been made in the last years. But it's also tightly related to the Affine Deligne Lusztig varieties we look at later. So that's why I want to formulate it. And it's called reflection length. So what's that? So first, you have your standard generating set S here, which is a particular class of reflections in your Coxeter group. And you can look at a much bigger generating set by looking at the set of all reflections. So whenever you see a hyperplane in this picture, you take the reflection along it. So what this formally is, you take all elements in your group and conjugate your generating set by it. This is all reflections in W. And then you can ask, what is the length of an element little w in capital W with respect to this new, much bigger generating set? So this is the minimal number of R in capital R needed to write little w. And, for spherical ones, it's known what reflection length is, in the sense that you can read it off of a minimal presentation. But for affine ones, only bounds are known. So, okay, let me state a general theorem by Dyer. I think it's from 2001. So here, WS is an arbitrary Coxeter group. Then you can you can rewrite this reflection length in the following way. You take a minimum over an index P, where the following happens. You write your element W in a minimal way in S, so S1 to Sn, a minimal presentation for W. And then you delete letters Si1 to Sip somewhere in your word. And by doing so, you hope you end up at the identity. So let me put it like this. Okay, and the minimal number of letters you have to delete in order to end up at the identity, this will give you the reflection length. So that's for arbitrary Coxeter groups. But if you're in an affine Coxeter group, meaning the space you're acting on is some affine space R to the n, in particular you're infinite, then a priori it wasn't even known whether this length function is even bounded on your group. So you have an infinite set, so theoretically it could be unbounded. And in hyperbolic case, it actually turns out to be unbounded by a theorem of Dushenko. But here we know that there's a bound. It's less than or equal to 2n, where n is the rank of your group minus 1. In other words, it's the rank of the corresponding spherical group. And you also have a lower bound, which is given by the spherical piece. So if you write this as T lambda times u, as we've done over here, then your local spherical direction, the reflection length of this one, is a lower bound for the reflection length of the affine one. And this is due to McCammond and Peterson. And it's from, I think, 2011. So that was the best possible known thing. And so one thing I want to show you now is that this interpretation of Dyer's can actually be rephrased in a geometric way using galleries. So let me introduce galleries. So you take your tiled Rn or Sn, so the space your Coxeter group acts on, so you have W fixed. It comes with this tiling. And the gallery in this tiling, it's a sequence of maximal simplices as follows. So of course we start somewhere in some simplex. So I don't know, let's put C0, this white fundamental simplex over here. And then you keep going, you add a bunch of maximal simplices. And we give them a name, they're called chambers. And then you go, okay, so you have this one, and then you take another one, and you might repeat it, and then you go to the next, and so on. So, but we want to know a little more than that. We also want to record which walls we've crossed from one to the next, and impose the condition that they're not kind of randomly distributed all over the place, but that the consecutive ones share a codimension 1 phase. Okay, so C0 contains some P1, which is a codimension 1 phase of both C0 and C1, and they're also called panels, these codimension 1 phases. And then C1 contains another P1, and you end with a Pn in Cn. So now you might ask, what if I repeat a chamber from one to the next? They, of course, have a codimension 1 face in common, but they have many codimension 1 faces in common. And the point here is you choose one. Okay? So you kind of, even if you repeat, so if Ci minus 1 equals Ci, then Pi is a fixed of the many codimension 1 faces they have in common. Okay. So while doing so, you learn that a gallery has a fixed word associated to it. By word, I mean the word in the Coxeter group W. And this word we call the type of the gallery. And so how is this done? Show you a picture. So you have a gallery. To make it easier, I'll take a minimal gallery. I hope you can see this green on green. So you start at the identity, you cross to the next chamber. What you've crossed here is a red face. Okay? And you can color in all the faces of the plane by the generators. Okay, this red here, this corresponds to the generator R. Why? Because I get to this chamber from this chamber by a reflection along R. With the same principle, I can color in this codimension 1 face and name it S, because I get from here to here via S. And then this one is left white, it corresponds to T. Okay, and using the group action, I can color in all the faces. So as you see, this green gallery here becomes a type of red, white, purple, white, red. And this would be the sequence of these, the colors of these codimension 1 faces they consecutively share. Now I lost white. So here red, white, then purple, and so on. Okay, so you can associate a word to it. So it is good because there we have words. And then you can try and figure out what it means by deleting things. So deleting things in your word essentially means that you have the possibility to cross somewhere, say red at this final step, but you're not doing it. Okay, so you walk over here, then you could have crossed along the red, but you don't do it, so you stay in this place. So deleting things means that you have panels where you repeat chambers along a certain color. Okay, so this decorated word here corresponds to a gallery with repeated chambers. We give those a name. We say a gallery is folded at I or at Pi if Ci minus 1 equals Ci. Okay? So what that means is in the corresponding word, this particular generator is decorated with a hat. Okay, so you can rephrase Dyer and say this length is the minimum number of folds a gallery of type W, and I put an arrow because here you really need to fix this word you picked for W. that runs from the identity to the identity. Okay, so I told you how to get from a gallery to a word, but I haven't told you how to get from a word to a gallery. So the correspondence is not one-to-one. What you need to pick is like a start place. You can start at any triangle with a given word and produce a gallery. But what we do here is we always start at the identity. That's like your natural starting place. And then it's one-to-one. Once you've fixed the starting place, each word gives you a unique gallery. Okay, so you could, in order to explicitly compute reflection length, compute number of folds of galleries of fixed type. Okay, let me take a little detour to buildings to show you that these galleries, the folded galleries, arise very naturally in buildings. And they arise from retractions. So here's what a building is. You take a simplicial complex that's covered by subcomplexes. They're collected in an atlas A and called apartments. And this complex is a building if the following holds. So for one, each of these subcomplexes should be a Coxeter complex. So all A in A are Coxeter complexes. So they become the building blocks of your buildings. So you glue together Coxeter complexes. And you do it in a way so that this A is very rich. So for one, for every pair of simplices, C and D in X, you assume that there is an apartment containing both of them. So there is an A in script A such that C and D are contained in A, or elements of A. And then you want it to be regular. So whenever you can find two apartments containing the given simplices C and D, then you want them to be isomorphic. So there exists an isomorphism from A to A prime such that the intersection, so in particular C and D, is pointwise fixed. Okay, here's an example. So a slightly smaller reflection group than the one we were looking at are infinite. No, the reflection group is a line, but the building associated to it are infinite trees. So the Coxeter complex of a line, it's generated by two reflections. This is our base apartment. It has a Coxeter group associated to it. And you have, say, valency 3 everywhere. So you branch with valency 3 at every vertex. Then again, they come in two colors. So white and green. Okay. Okay, that's good. And we can look at galleries ignore that there's a whole tree. We'll look at galleries in this Coxeter complex. So we have to put the identity somewhere, say it's here. And then say look at a gallery of length 3. So here's the 3 chambers, 1, 2, 3. And then we use retractions. So what are retractions? Retractions are maps, distance non-increasing maps from the tree to itself. But not onto the entire tree, but onto this base apartment. So we have a map from X to A, and we have another map from X to A. One is based at, say, infinity. So what you do is you pick a direction at infinity. Say this one. Okay, so this base apartment here, if you keep going, it points to a point at infinity. And there's a natural way how you can collapse the tree onto an apartment with respect to this direction. Namely, you think of holding up your tree at this end point of the ray. So what happens is all the branching falls down and gets smashed onto your base apartment A. So you could also think of driving with a large truck from here to there, and then everything just gets flattened out this way. Okay, so rho flattens everything into the opposite direction of infinity onto A. And then there's a second retraction based at the identity where you flatten out towards infinity. So you stand in the middle, and then going left and right, you smash everything out onto A. So this part of the tree gets flattened out to here, and that part of the tree gets flattened out over there. Okay, so this retraction R splits your tree in the middle, sort of, and flattens things out to the left and right. So the game now is you take pre-images under R of this red path. So you end up 1, 2, 3 with paths like this. This one, for example, or this one maybe, and there's more. Okay? And the longer your paths get, the more pre-images you see. And then you take the image under this other retraction. So in the end, say you take this pre-image, and then the image of the green path under rho flattens everything out to the left. So you end up with a path that starts in this direction but then walks 2 steps in the other direction. And what you've created is a fold at this panel. Okay? So this was a little detour to show you that they really kind of come from the intrinsic structure of these buildings. So for what we're going to do next, it's not enough to know that there is a fold somewhere, but we also need to know in which direction this fold goes. And we want to introduce the notion of a positive or negative fold. So how do we come up with an orientation of folds? Well, we orient half spaces of our entire space. Let me So an orientation here really corresponds to a position of the sun. Okay, so what we do is we pick an element, call it U, in the spherical Coxeter group. And what we want to orient is the corresponding affine Coxeter group. Or actually Coxeter complex So this is the corresponding spherical one. We pick an element, but picking an element is the same as picking one of these 6 cone directions. Okay, so here the elements, they label the maximal simplices in this sphere, but they're in one-to-one correspondence with the cone directions corresponding to the reflection hyperplanes of this spherical group here. So you pick a direction, say you put the sun here, and then you say, okay, each of these reflection hyperplanes corresponding to your generators that belong to the spherical part separates your space into 2 half spaces. And you say a half space is positive if it contains the sun. Okay? Or the side of the wall is positive if it faces the sun. So this side would be positive, this would be negative, this side would be positive, and then this side would be positive. Okay, so we really contain subsectors of this sector here. Okay, so we've oriented those, and then just doing things periodically, we can orient any of these half spaces we get if we introduce more reflection hyperplanes. Okay, so positive side of the hyperplane faces the sun. So this is the sun. And extend this periodically. Okay, but I promised to orient folds, so we somehow have to go from here to folds again. Well, you have your gallery, starts somewhere, it has a fold somewhere. And then if it has a fold somewhere, there's this panel at which your fold happens. Okay? You remember in your gallery you recorded the shared faces. They corresponded to these codimension 1 faces. So you can take the span of your PI. So a fold at I is positive if the repeated face, the repeated chamber, so Ci minus 1, which is equal to Ci, is on the positive side of the hyperplane you're folding at. And the hyperplane you're folding at is the span of Pi. Okay? So now for each fold in the gallery you can decide whether or not it's positive or negative, given a fixed position of your sun. And it really depends on the sun. Okay, so here, for this sun, this fold is positive. But if I had put the sun up here, then it would be a negative fold. Okay, so a fixed gallery is positively folded only with respect to a fixed choice of an orientation, which is a fixed position of your sun. Okay, and then what can you do? You can play a game in this tree. You can fix a sun, and say here, and fix a red minimal gallery in A. And you then take all the pre-images under R and all the images of those pre-images under rho and look at the set of end chambers you can get to. So this gallery gets you from 1 to here. And then one of the things you obtain playing this game gets you from 1 to here in a folded way. So in this particular case, there's not much more you can do. You can also fold this bit over here, but that's all. Okay, so there's 3 places you can get to. There's this one, and this one, but there's a hole at the identity. You cannot fold your red thing back to the identity just because of parity. You would need something of even length to get back folded in half. But here it's of odd length, so you cannot do this. Okay, we will see this game again in a second, but let me first show you ways to get folded galleries. So here's an explicit construction you can do in any affine Coxeter group. You can look at this particular point over here, which is this translation, t to the 2 rho, and rho is half the sum of the positive roots. For those who know about root systems, they know that this t over here is just a co-root lattice, and that this black point over here is a very particular point in the co-root lattice you can explicitly describe in any type. And what we fix is a minimal gallery from the identity to A, where A is this particular element, t to the 2 rho, times the longest element in your spherical group. So the spherical Coxeter groups, they have a unique longest element, and you pick a minimal gallery. And then, depending on a presentation, a fixed presentation of W0, you can fold this gallery. So we first fold along this blue hyperplane here. What this does is it gets us from this minimal gallery to this folded gallery. So it's now folded at this panel where it crossed this blue hyperplane. And the rest of the gallery is the reflected image of the rest of the original gallery. And then we fold again along this horizontal hyperplane. And again, we keep the initial bit, and we reflect the remaining bit along this hyperplane here. In terms of words, this means we put a head on the generator that corresponds to this panel. Okay? So if you remember Dyer's reformulated theorem. So, and then another fold appears along this diagonal hyperplane again to get a third fold. And we end up with this minimal gallery here that runs from the identity to the identity, is of the same type as the one we started with, but has 3 folds. Okay? So that's, as you can see, it's not the minimal way of folding. You could have folded along here just once and also put A onto the identity. So reflection length would be 1 here, but for the Affine Deligne Lusztig varieties later, we will need the one with 3 folds. So that's a way of combinatorially producing explicit folded galleries. And then you can manipulate them. So here's our little folded friend again from the previous slide, just rotated by 60 degrees. What you can do is you can apply a translation B. So B translates the identity to here. And then you have your little guy up here. And this has the property that you can extend it at the beginning with a minimal gallery connecting the identity to B, so that the unfolded gallery from the identity to now X is minimal again. And you have produced a gallery of a much longer type that also has 3 folds. And you can see the direction of the fold stays the same. So if we say put the sun down here, this was positively folded. Every fold goes towards the sun. And then also this one is positively folded. So we keep control over the direction of the fold. Okay, here is an image that just should tell you that there's methods from representation theory. They're called root operators that produce from this blue gallery a whole family of other more complicated folded galleries, all of which have 3 folds. And again, we keep control over the direction of the folds. So they stay positive when they were positive. So there's explicit ways of constructing entire families of positively folded galleries. Okay, here again is a picture of the game we were playing in the tree. I cannot show you a picture of a two-dimensional building with these apartments as building blocks, but what I can assure you that these red maximal simplices, these red chambers, they're obtained the same way as here. So again, in this big building, which is now a gluing of two-dimensional R squares, all tiled with the equilateral triangles, in satisfying these axioms, you again have a retraction that's based at the identity, and the identity in this picture is here. And there's a retraction based at infinity. Infinity would be up here. And if you play this game, take pre-images under R, take images under the retraction based at infinity, and you start with a minimal gallery that connects the identity to X, all the places you can get to are colored red. Okay, so this picture I stared at in my thesis and tried to describe the pattern of these red things and miserably failed. And many years later, in a conference in Oberwolfach, Ed Thomas showed me the picture on the right and said, you know, someone said this should have to do with retractions in buildings. I said, yes, it has. But at first we didn't understand how. And this picture appeared in a paper on Affine Deligne Lusztig varieties, where they produced it with a computer program doing explicit calculations in SL3 and trying to figure out which Affine Deligne Lusztig varieties are non-empty. So the gray things on the right, without having you told yet what an Affine Deligne Lusztig variety is, describes collection of non-empty Affine Deligne Lusztig varieties where the y, this index y here, varies, and for every y where this guy is non-empty, it's colored gray. And if you stare at it for long enough, you can see the following. There's this red ship over here, and there's a gray ship here turned sideways. And all the red things fit into the gray picture if you turn them like this and put the ship on the ship. It looks like a miracle, but it's actually, we can actually make sense out of this. So that was the starting point of this joint project. And here's what Affine Deligne Lusztig varieties are. We fix a bunch of notation. So you take a finite field of prime power order, you take the Laurent series of an algebraic completion of this field in the variable t, take a discrete valuation in its ring of integers, so O is the polynomial ring. And then there's, of course, a projection of O onto the algebraic completion you started with, which is putting your variable to 0. Having these things, you can define an affine flag variety associated to a connected reductive group. So if you have never seen connected reductive groups, just think of SL3. So SL3 gives you the equilateral triangle example we've been looking at. So let's take example here. So G, say, is SL3. Then your Borel becomes the upper triangular matrices, or SLN, and then upper triangular matrices. Your torus becomes diagonal matrices, and this, the group I, which is the pre-image under this projection of O onto K of the Borel group, where you plug in K instead of F. So this becomes the following. Multiplicative on the diagonal, T to the O below the diagonal, and O above the diagonal. So, yeah. Okay, and associated to it, there's a while group, and this while group happens to be a Coxeter group. So let me just write down the while group. Actually, you have two. You have a spherical Weil group, which is the normalizer in G of T of F over T of F. And then you have an affine Weil group. So this is, again, the normalizer of G of T of F, but now mod out T of O. Okay, and this, let me just draw it like this. This is this, sorry, hexagon, and this is the A to tilde tiling. Okay, so this is the example we've been looking at. Okay, and then the variety in question is this object here. You make use of the fact that your group G can be decomposed like this. So you have this group, this mysterious group I, and the disjoint union over all elements X in the affine Weil group, which is this Coxeter group, over those double cosets gives you back G. It's not that mysterious if you know the building theoretic interpretation. So it turns out that the B from the previous slide is the stabilizer of the sun at infinity, and the I is the stabilizer of your chamber labeled identity in the automorphism group of your building, which is this algebraic group, contains this algebraic group G here. So if you take the stabilizer in G of the identity, this is another description of this mysterious group I. Okay, so it really has a geometric meaning. And then this double coset becomes a geometric meaning. So you can identify this chamber with I itself, and then left images of I are other chambers in your building. So here, this actually is this double coset IXI is a certain subset of the chamber set of your building. Okay, so here we ask if a certain sigma conjugate, so it's not exactly the conjugate of this element B, but it's twisted by this Frobenius automorphism sigma on the right, is contained in this particular subset of chambers. Okay, this, if you plug in the field F being the Laurent series, turns out to be an algebraic variety, and it's called the Affine Deligne Lusztig variety, and it's indexed by a pair of elements X and B. And in fact, you can prove, and it's not that hard, that both X and B can be chosen to be elements in W, because every B has a sigma conjugate that's contained in W, and also those are isomorphic if you replace one of the indices X and B by a sigma conjugate. So you can think of this variety as something indexed by two triangles in our equilateral tessellation. Okay. So the main questions are the following: non-emptiness and dimension. So they're the most basic questions you can ask, but up to now they're not fully settled. So a lot of work has been done by many people. So Gertz, Haynes, Kottwitz, he are maybe the most important ones. In 2014, he settled the dimension formula, and also the non-emptiness pattern was settled for a subclass of the possible B. So let me tell you what this subclass is. So an element B in this group, but it's by definition basic if it's sigma conjugate to an element of length 1 in the extended affine Weil group. So the extended affine Weil group is, instead of taking the spherical Weil group in a semidirect product with a co-root lattice, you take it in a semidirect product with a co-weight lattice. So what you get is a finite sheeted cover of your Coxeter complex, where the number of sheets equals the number of different types of special vertices in your complex. But that's, for us, for today, maybe not all that important. What's important is that whenever you have two basic B, they're sigma conjugate. So the corresponding affine Deligne Lusztig varieties XXB and XXB prime, they're isomorphic. So asking about non-emptiness and dimension, it's the same question. So you only have to solve one of the basic cases to answer the non-emptiness and dimension question. And the basic elements in this particular example we've been looking at, they're all colored blue, and the black one is the identity. That's basic as well. Of course, the identity is sigma conjugate to the identity, which is of length 0. So that's the case that's been solved. And then the case we were looking at are the pink ones. They're the translations, meaning that in this description of your elements here, as a translation times the spherical element is the identity. So you just translate your fundamental alcove, your fundamental chamber somewhere. And those are pairwise not sigma conjugate. So each of the pink ones is a separate case. Okay, so before showing you this, I'll show you the theorem that produces all the results. So the trick was to use this building interpretation I've alluded to in this picture of these double coset IXI as a subset of the chamber set of your building, to use it in order to determine non-emptiness and dimensions. And what one is able to prove is the following. That's, say, the geometric approach to the affine Deligne Lusztig varieties. Again, W is an affine Coxeter group. And then for any X and B some translation in W, that means B is of the form T times T lambda times the identity. We have that the non-emptiness of this variety is equivalent to the existence of a positively folded gallery gamma that runs from the identity to the translation B and is of type X. So you have your two Weil group indices here, one of which determines the type of your gallery, and the other one the end chamber. And not only this, but also the dimension of this variety is essentially given by number of positive folds plus the number of positive crossings. I have not yet told you what a positive crossing is. It's obviously not a fold, so Ci minus 1 is different from Ci, but you walk from the negative side of a wall to the positive side of a wall. So Ci minus 1 is on the negative side and Ci on the positive. Okay, so that's it. So the proof really goes like this. You have this definition of your variety. You have this double coset here. You kind of view this as possible pre-images of R under a minimal gallery of type X, and then show that you can actually determine the non-emptiness by these positively folded things, and then you have to work a little harder to see that your dimension is also encoded in this description of this gallery. Okay, we've already seen proofs of theorems of the form this variety is non-empty. and has dimension x. Knowing this theorem, in order to actually prove non-emptiness theorems about specific affine Deligne Lusztig varieties, what you have to do is you have to come up with positively folded Garys of a certain type ending in a specific position and count their folds and crossings. Okay, and we've already done so. So here, for example, we've constructed a gallery that runs from the identity to the identity, has 3 folds, and is of a certain type. We perfectly know what it is. So this implies that this variety, using this theorem here, is non-empty and has dimension at least 4. Why 4? We put the sun down here, so on lower left-hand side, then all these 3 folds become positive. And there's one positive crossing, the one that gets you back from here to here. And they sum up to 4, so that's a lower bound of your dimension. And we've seen more theorems. So here, for example, this slide shows that from non-emptiness here, you can deduce non-emptiness of xb with this x and this b here. Okay, so there's combinatorial methods that take place in the plane, so in a single Coxeter complex, that produce your theorems about affine Deligne Lusztig varieties. And let me get back to finish this talk to the question we started with. It's no longer here. So using now non-emptiness of affine Deligne Lusztig varieties, we get back something about reflection length. So as a corollary, we obtain that the reflection length of elements of this form, you have a translation times a Coxeter element. So this is just the product of all generators of the spherical group. That this turns out to be n, which is the rank of W minus 1. So here W is affine, and this is a Coxeter element in the spherical piece. Okay, so this we first obtained as a corollary of all the affine Deligne Lusztig business, and then I thought, well, this is overkill. You really have this algebraic machinery to solve this innocent problem here. But knowing that this is true, I was able to give an elementary proof of this fact. And let me stop with this. Thank you.
Thanks for the beautiful talk.
Thank you.
Is there any question, comment? Yes?
So it seems that from the description you gave in this estimate that the dimension of x, b, y, b should be at least the one of yn. One should be very pessimistic, right? I mean, you have all this path going up to b. Isn't this positive?
Isn't it what?
I mean, aren't all these crossings positive?
No. So here, in order to have those crossings positive, you have to put the sun down here.
Okay, so they are not.
So they're all negative, in fact, for this particular example. But sometimes, okay, so I picked this example where it really turns out to be equal in the end. If you're not in the fundamental region, like the one that contains the identity but something else, then things get more complicated. Then, of course, you add things that are positive, which you should not add for the dimension. Then you need correction terms that depend on the global direction of your x.
So that's the essentially.
Yeah, this is the essentially part. But we have like an explicit formula. Given x and b, you can compute it, but sometimes you have to add correction terms. Yeah, for precisely this reason.
We postpone the questions for the tea because we need to move on to the next talk. So let's thank Petra again.
Thank you.